In this lecture, we will learn about interaction of radiation with matter and condition of lasing action. What conditions are needed for lasing action? The story of laser started in the second decade or the first decade of 20th century when Einstein gave a theory of interaction of radiation with matter. At that time, there was no way to obtain the lasing action, but Einstein predicted. This shows the vision of the scientist, great scientist. In this unit, we have laser amplifier, amplifier gain, amplifier phase shift, amplifier power source, rate equation. We also have 4 and 3 level pumping lasing scheme, examples of laser amplifiers, characteristics of laser output, power spectral distribution, spatial distribution, mode selection, gas laser, CO2 and N2 laser, solid state laser and YAG laser, excimer laser, semiconductor laser. Overall, we have 4 and 3 and 4 types of laser and various lasing scheme in this unit. We will learn about this. First and most important thing is how laser can be produced. The basics we will learn here. We will be able to learn basics of interaction of radiation with matter. Also, we will discuss stimulator emission and condition of lasing action. First and most important thing is what is laser. I think all of us will now we know the laser. Laser is a device that emit light. You can say many devices emit light. What is the difference? Yes, this emit light through a process of optical amplification, which is based on stimulated emission and of electromagnetic radiation. As this clear, basically the laser word is an acronym and it is L A S E R. L for light amplification, A for amplification, S for stimulated emission, E and R for radiation. Here we amplify the light. What light we amplify? We amplify stimulated emitted light. How this is important, why it is important, we will discuss in this chapter. The laser is highly intense and very less diversified, almost negligible diversified beam, sharp beam, which can travel long distance, few kilometers. Laser is a device that stimulates atoms or molecules to emit light at particular wavelength and amplifies that light, typically producing a narrow beam of radiation. The emission generally covers an extremely limited range of visible infrared and UV wavelength. Many different types of laser can be developed with highly varied characteristics. Important thing is how we stimulate the system and how then the stimulated light can be amplified. Do you know when the first laser was built? It built in 1960, almost 60 years back by Mayman. Mayman developed the first laser, that is ruby laser. We will discuss detail of ruby laser in the coming lectures. Theodore H. Mayman at Hughes Research Laboratory, based on theoretical work by Charles Hart Tones and Arthur Leonard Schwellow, he built laser. Laser always is interesting for all of us due to the colors and the specific properties. But since the birth of this laser, it always have some controversy also. There is a very interesting story about laser. When it was invented in 1960, Washington Post published this report as a negative way. They quoted a death ray invented by the Mayman in 1960 today. Why it was said? Initially, the people thought, the researcher thought, after observing the many characteristics, interesting characteristics of laser, then it may use to kill the persons. And it was shown in many Hollywood movies also, the laser gun which can kill the persons. But then after development, many new applications developed, and slowly, many new applications. Now we are using these applications in hospitals, in eye surgeries, and many other surgeries, non-opening surgeries. Apart from surgeries, it can be used for tagging purpose. It can be used in barcoding in many malls, in almost all the malls. It can be used for storage device, hard disk, not only hard disk, balki it's a CD, compact disc, then DVD, then Blu-ray. So many applications we have. Basically, a laser consists of two mirrors, full mirror and partial mirror. This is full mirror. On other side, we have partial mirror. It's not. We generally, from partial side, we extract the result, the output. Then we have cathode and other specific places. We have developed laser 60 years ago. Other than this, it has a long history. It has been developed in 1960, but first ever thought by Einstein in the first decade of 20th century by Einstein. Einstein was the first person who thought ever on such type of light. He developed what happened when light interact with matter. On the base of those thoughts, the laser has been developed. The laser is an outgrowth of a suggestion made by Albert Einstein in 1916 that under the proper circumstances, atom could release excess energy as light, either spontaneously or when stimulated by light. Then, at the time of, he was not having anything to visualize these such type of radiations, but in 1928, Rudolf Falkner Landberg first observed stimulate emission, although at the time it seemed to have no practical use. Then few after 28 to 38, 48 and 23 years after, Charles Stones at Columbia University in New York thought of a way to generate stimulate emission in microwave frequencies. At the end of 1953, he demonstrated working device that focused excited ammonia molecules in a resonant microwave cavity where they emitted pure microwave frequency, and that is called maser, microwave amplification by stimulate emission of radiation. Alexander Mikhailovich Prokhov and Nikolai Gandhievich Basov of the PN Lebedev Physical Institute of Moscow independently described the theory of maser operation, and for this they shared 1964 Nobel Prize also. Laser have become standard tool in diverse applications. We use laser pointer in presentation purpose in pointer in lecture halls, and laser target designator guide smart bombs to their target. As a target it can be used. Laser weld razor blades. We can get a right pattern on objects on production lines without touching them. We can remove unwanted hair. Laser technique is used for this. And bleach tattoos. If you want to remove tattoos, you can use this laser method. Laser rangefinder is the space probe profile the surface of Mars and asteroid Eros in unprecedented detail. In the laboratory, laser have helped which is to cool atom within a tiny fraction of degree, absolute zero. Laser have many applications in the lab, in the society, up to astronomical uses. Today, we will discuss the first introduction of this laser, interaction of radiation with matter, which was given by Einstein. Actually, laser emission is shaped by the virtue of quantum mechanics. Quantum is began in the beginning of 20th century by Planck and then used by Einstein. This quantum mechanics limits atom and molecule having discrete amount of stored energy and depends on nature of atom or molecule. The lowest energy level for an individual atom occurs when its electrons are in nearest possible orbit to its nucleus. If we see the electronic configuration, basically electron configuration means the arrangement of electrons. This condition is called ground state, where electrons live normally. When one or two atom electrons absorb energy, they move to outer orbit. That atom is called excited atom. Normally, the excited states are not stable. The ground states are highly stable but not excited. And if these are not stable, what it means? It means immediately electron drop to higher level to lower level. They emit extra energy of light. Here, three figures are shown, three conditions are shown. And as a consequence of quantum mechanics, discrete levels are shown. E1 and E2 are the discrete levels, where we are showing E1 as the ground state, E2 as the excited state. On E1, when the atom is at ground state, you send a photon, and this photon send this electron to higher energy state. This is called absorption. Absorption means something is absorbed by the material. We are discussing here interaction of radiation with matter. Radiation you can send on matter and it will be absorbed. As we have discussed in the last slide, the excited level will not have too much lifetime. Actually it is an unstable state. So the electron immediately move to ground state, and when it moves to ground state, so it emit a photon. Similarly, if you go to other a higher state, it absorb photon, but you move to ground state from the low higher to lower, it emit photon. But this process is called spontaneous emission, which normally happens everywhere. Spontaneous means by their own way. It is moving to the ground state because not because of others, but because of their own nature. It can't live for a long time on the higher states. But I seen suggested third one. Here we will discuss this in detail. Sometimes there is a possibility you send one photon on the excited atom and immediately it move to ground state and give you two photons. The photons are identical in all respect. This is stimulated emission. Einstein recognized that this emission could be produced in two ways. Usually, discrete packets of light known as photons are emitted spontaneously without outside intervention. Alternatively, a passing photon could stimulate an atom to emit light. But there is a condition. The passing photon energy exactly matches the energy that electron would release. Then it's called. So it move again, immediately move to ground state, and this is called stimulated emission. Now, which process dominate depends on ratio of lower energy to high energy configuration. Remember this, we will discuss it in detail again. What is the population of excited state? What is the population of ground state? These two things are very important later. Ordinarily, lower energy configuration dominate for no common samples, for a common examples and all the materials. If the atoms are normally want to live in lower energy state, this means that spontaneous emitted photons is more likely to be absorbed and raise electron from lower to higher level, and then to a higher level energy configuration, then to stimulate a high energy configuration to drop. And that is why the more common is spontaneous, not simulated. Discuss this event in way. Suppose we have absorption. You send the photon and it absorbs, and this absorption is h nu. The number of possibility of how many will be absorbed is proportional to that. N1 is, suppose N1 and N2 are the population of ground state and excited state, and you are applying Q photon density for time interval del T, then NAB possible absorption probability is equal to N, proportional to N1. N1 is the number of atom in ground state. This NAB is also proportional to del T, the time duration for which you are applying interaction. And this NB also proportional to Q, the applied energy. If we combine this all, then we can combine this to get this. NAB is equal to, is proportional to N1 del QT, and if you use equal sign, then you will get this B12. This B is called Einstein coefficient of absorption. Another process is called spontaneous emission. This process is followed by the first process, absorption. After absorption, the atom moves to this state, higher state. Now the lifetime of this state is very small. So immediately it moves to ground state by emitting a photon. And this is called spontaneous emission. Spontaneous means by their own way, no force is there. This spontaneous emission is proportional to time interval during which you perform this. This is also proportional to N2. N2 is the number of atoms at excited level. Mind this. And if you combine this, then you will get this. And SP is equal to A21 N2 del T. A21 is called Einstein coefficient of spontaneous emission. Now the third thing is stimulated emission. Stimulated emission means whenever you give the energy, electron move to excited state. Now at this state, before the electron start to move to the ground state, if you can supply a photon of the same energy difference and on this excited atom, then this excited atom immediately move to ground state. And in this process, one photon will be delivered by the electron, and second is you applied, you sent. So you have photons here in place of one. This is called stimulated emission. This stimulated emission also called forced emission, because the electron was in excited state, and your another photon forced that electron to move to ground state. In this case, stimulated NST is proportional to T, NST also proportional to Q, and N2. If you write these values here, then you can write NST is equal to N2 del QT or is equal to B21. These processes are also summarized here. Spontaneous emission. First is stimulated absorption, what we have discussed here. Atom move from lower to higher. Then stimulated, you send one photon, so it move to two identical, and third one is by their own way. The interesting thing about this stimulated is these two are identical. These two photons are identical. Identical in all respect. Identical means they have same energy, same state of polarization, same frequency, and will move in the same direction. If you can amplify these signals, then you can create large number of photons in the same direction, same state of energy, and same direction, same polarization. This is useful for laser action. If we combine our equations 1, 2, and 3 about NAB, NSP, and NST, then we can generate condition of lasing action. For this, you just get the ratio of NST over NAB and NST over NSP. You will get these results. For lasing action, the minimum requirement is this ratio, both ratio should be greater than 1. It means estimated emission should be more than an spontaneous or an absorbed. If you do this, you will get these conditions. One condition is called N2 must be greater than N1. That is called, from the first condition we have drawn, N2 greater than N1. It means the number of atoms in ground state must be less than number of atoms in the excited state. We have to populate higher levels than lower levels. That is lasing importance. And that is why Einstein didn't got any success in that era, because there was no way to learn this, how it can be great. After the invention of and metastable states, we were capable to study or try for for this population inversion. And the second condition must be Q must be high. You have to apply very high energy if you want this. These two are the limitations also, and on one side it is limitation, then Q must be high, and then it has been shown here, when you give the energy, these called the atom called excited atoms, and in excited atoms you can give more photons, so this will give you more photons in the same direction. Suppose you have three photons, you have three atoms, then you will get 6 photons in the same direction. By this way, we can increase the number of simulated photons. By comparing this, we have obtained the results. If we compare this result with Boltzmann statistics results, then we will get these values. Then A21 upon B21, where A21, B21 we have assumed these are the coefficient of Einstein, A21, B21, B12, and A21 over B21 should be equal to 8 pi h nu cube over c cube. And this is the relation between these coefficients.